Alright, so this time we're going to be talking about exponent rules. So what I'm going to do is state the rule and then show why it's true, and then maybe show you an example or two of it in action. So the first rule is when we have two powers multiplied together. So it looks something like this. So a to the m, the first power, times a to the n. So what you'll notice is that the exponents are different, but the bases here are the same. So an example of this would be, say, if I had x squared times x cubed. Okay, so let's look at this. X squared, first of all, is the same as x times x. So right here, this is x squared. Multiplied by x cubed is x times x times x. So this here is x cubed. So this expression is the same as this. Well, this one right here, you might just notice that I have 1, 2, 3, 4, 5 x's multiplied together. And 5 x's multiplied by each other simplifies to just x to the 5. So x squared times x cubed is x to the 5. If we look at what we started with, was there any kind of clue as to what our answer could have been? Well, if you look at 2 and 3, well, if I add 2 and 3, I end up getting the 5. And the reason that we add the exponents in this rule here is because, your expression ends up looking like this, where you just have that many x's multiplied by themselves. And that ends up with x to the 5 there. So the general rule up here, when I have a to the m times a to the n, that can be written as a to the m plus n. Okay? So anytime you have a situation like this where the base is the same with different exponents and they're multiplied, all you need to do is add the two exponents together, no matter what they are. So let's look at another example of that in action. How about let's make the numbers not as nice this time. So let's say we have x to the 1/2 times x to the 2/3. Well, in this case, I still would do the same thing. I still would add these exponents together. So all I would need to do is add 1/2 and 2/3. So 1/2 plus 2/3. In order to add fractions, remember we need to get a common denominator. So a common denominator between 2 and 3 could be 6. Of course, 2 times what gives me 6? Well, 2 times 3. So that means I need to multiply the numerator by 3 as well, and 1 times 3 gives me 3. 3 times what gives me 6? Well, that's 2. And then 2 times 2 gives me 4. And now that I have my common denominator, all I need to do is add my numerators together. 3 plus 4 gives me 7/6. So this tells me that this is equal to x to the 7/6. Okay, so that's the first rule. And that's when we have the two expressions here multiplied. So over to the side here, I'll write a to the m times a to the n equals a to the m plus n. So that's our first rule right there. So that's if they're multiplied. But how about if they're divided? Because, of course, the opposite of division is multiplication. So let's look at an example like this. Say if I have x to the 6 over x squared. So these two things are divided. They have the same base, but the exponents are different. So in this case, I can rewrite x to the 6 as x times x times x times x times x times x. I think that's 6 over x squared, of course, can be written as x times x. Looks like a lot of x's, but now, since we have a fraction, what I can see is I can pair up this x on the bottom with this x on the top. And x divided by x, well, any number divided by itself is always 1. So that means these can cancel out. Another pair of x's can cancel out right here. They cancel. And that leaves me with just 4 x's left on top. So this must mean then that x to the 6 divided by x squared is equal to x to the 4. Of course, that means that the final answer is really just the top exponent subtract the bottom exponent, right? So the general rule is that when you have a to the m divided by a to the n, then that means it's equal to a to the m minus n. Okay? So you might now be asking the question, well, what if the exponent in the denominator is bigger than the exponent in the numerator? Well, nothing really changes. The same thing happens. So let's change the exponents to this. So x squared over x to the 5. Well, if I were to do it the long way, I could still write this as x times x over x times x times x times x times x. These x's would cancel off, leaving me with 3 x's on the bottom, right? So this leaves me with 1 over 3 x's, so 1 over x cubed, right? Well, what you might notice is that this expression right here, since this thing is in the denominator, I can also rewrite it as x to the minus 3, right? Remember our negative exponents from the past. And if I take 2 and subtract 5, I get negative 3. So this rule still works even when the numerator is smaller than the numerator's exponent is smaller than the denominator's exponent. So that's the second rule. That's when you have division of powers. Let's look at the next one. This is when you have a power raised to another exponent. So it looks something like this. Let's say I have x squared, and that gets raised to the 3. Well, we'll do the same thing that we did in the previous part. I'm going to rewrite x squared as x times x. And then that gets cubed. Alright, well remember, cubing something means multiply by itself 3 times. So x times x cubed is really x times x times x times x times x times x. Alright? And since everything is just multiplied here, I actually didn't need to write these brackets. So I can remove them. And when I remove them, I think it's pretty clear to see that this is just 1, 2, 3, 4, 5, 6 x's multiplied together. So this can be written as x to the 6. And if I look at the original, 6 is really 2 times 3. So that's the next exponent rule. Anytime I have a power, this is a power, raised to an exponent, I can multiply the 2 exponents. This also works for fractional exponents. You would just need to end up multiplying the fractions together. So as an example, let's say if I have x squared to the 1/5, it still works the same way. All I would have to do is take 2 and multiply it by 1 over 5. Of course, you could write that as 2 over 1 if you wish. 2 times 1 is 2. 1 times 5 is 5. So this is equal to x to the 2 over 5. Okay? So that is a power raised to another exponent. And the next two rules, I'm actually going to combine together and look at the same time. It will be when I have, actually no, we'll do one at a time. So let's say I have x times y raised to the 3. So what I've got is an expression with two terms, so x and y, inside a bracket, and the exponent is outside. So this is really a little bit similar to some of the previous stuff we've done. So what I can do is I can say, all right, well, this is going to be x times y times x times y times x times y. And that leaves me with x. In total, I've got 1, 2, 3 x's multiplied, so x cubed. Then in total, I've got 1, 2, 3 y's multiplied, so times y cubed. So what you might notice has happened is really both things that were inside this bracket here have ended up getting this exponent. So the x got the exponent 3, and the y got the exponent 3. Okay? So anytime you have something inside brackets raised to an exponent, whatever that expression is, everything that's inside the bracket gets the exponent that's on the outside. It doesn't matter how ugly it looks. So let's look at, say, x squared y to the 1/2 raised to the 5. So what will happen is these are two terms, x squared and y to the 1/2. Both of these things are going to get that exponent 5. So I will write it like this. The first term is x squared. It ends up getting that exponent of, not 1 over 5, of 5. The next term is y to the 1/2. It ends up getting that exponent of 5. And at this point, what you might notice is that we have this situation right here. We have a power raised to another exponent. So in this case, I could multiply those two exponents to give me x to the 10. I could multiply these two exponents, so y, you could write this as 5 over 1. 1 times 5 is 5. 2 times 1 is 2, so y to the 5 over 2. So that's more of a general rule. Anytime you have whatever is inside of here, it doesn't matter what this is. If it has an exponent outside of brackets, it has to get, everything that's inside the brackets has to get that exponent. So it doesn't matter if the terms were multiplied like that one just was, or if they are divided. So if I have, say, x squared over y cubed to the 2, both of these terms are going to get that exponent. So this is going to be x squared, getting that as well, and then the y cubed, getting the exponent 2 as well. And then using this rule again, I have x to the 4 over y to the 6. So this one is kind of similar to when it's multiplied. So the rule looks like this. When I have two things inside brackets multiplied, raised to an exponent, both things get that exponent. Or when I have two things inside of brackets raised to an exponent and they're divided, both things still get that exponent. So these two are really kind of similar to each other.